Hi there. For a while now I was looking for a mains power meter similar to the Hopi meter that you may know from Big Clive's YouTube channel, but much less expensive. Let's see if the content of this package can do the job. Okay, what we have here is a ring-shaped coil, actually a current transformer. And a module with 4 screw terminals and wiring instructions on one side and an LCD display on the other. And a piece of paper in Chinese. But with English instructions as well. The instructions are better than expected and include even dimensions for the required cutout to panel mount the module. A summary of the datasheet shows that the module is rated for 80 to 260 volts AC and up to 100 amps or 22 kilowatts, which is of course an overkill for my purpose, but it could be interesting for people with large solar converters. But just to be clear, this module works only with AC. It does auto ranging on current, power and energy readouts. The lowest power value is 0.5 watts and the lowest current is 20 milliamps. I believe the main difference to the Hopi display is that the power factor only has 2 decimals, where the Hopi uses 3, and voltage is shown only in full volts. Because I want to use this to build a Hopi meter replacement with its own input and output sockets, I bought the version with a closed current transformer coil for less than £11 delivered. If you want to measure current and power in existing cables, you can get a slightly more expensive variant with a transformer ring that can be opened, so you don't have to disconnect or cut a cable to get it through the transformer ring. The module is the PZEM-022 and made by a company called Peacefair. They do have a website showing their manufacturing areas and certifications and seem to be quite a professional outfit, so there is some hope that the unit is reasonably well made, accurate and safe. The wiring instructions on the back are easy enough to follow. CT is the current transformer coil and connects to the upper 2 terminals. The lower ones connect to mains AC. As you can see, one wire to the load is supposed to go through the current transformer ring. To test a device of unknown quality, the nice Peacefair website notwithstanding, directly with 240 volts mains is a bit of a gamble, so I would rather use an isolation transformer and a variac. Unfortunately, I don't have a variac and my AC transformer can only go as high as 24 volts, while according to the spec the module needs 80 volts. So I decided to run 2 transformers back to back. The first one is my bench AC power supply, set to deliver isolated 6 volts AC, which is fed into the secondary of a 12 volt transformer, so that its primary now delivers sufficiently high voltage to drive the module. The 12 volt transformer is rather small and can't deliver much power on the primary, certainly not enough to drive a decent test load in form of a 12 volt automotive light bulb. I feed that from the 6 volts instead. But of course this means only the current will be accurate, since the module assumes that voltage and current comes from the same source, and that's not the case here. But this setup is just temporary for the first tests. While the 6 volt circuit is safe to touch, the 100 to 120 volts AC voltage circuit is not. Although the high voltage is double isolated and relatively low power, you can still get a very nasty electric shock. If you try such a setup at home, you need to know what you're doing, and you do so at your own risk. The transformer you see is the 12 volt one, fed on its secondary via the red and black leads from the bench AC transformer. The primary are the 2 yellow wires that go directly into the module. The green wires tap the 6 volts AC to go to the light bulb, one lead going through the coil of course. The second red wire you see is going to the bench multimeter to compare the current with the one shown by the module. Turning the bench AC transformer on powers the circuit and the module comes alive. Unfortunately, I have no footage from the multimeter, but the 1.415 amps shown by the module is spot on. The glare on the display is from the protective film, which I decided to leave on while experimenting. As explained, the watt number is wrong because the module assumes the 1.415 amps happen at 100 volts. The power factor is 1 because an incandescent light bulb is a nice resistive load where current and volts stay in phase. The manual talks about a button, and there is this round thing on the right, slightly recessed below the level of the ribbed bezel. With a real hard squeeze, it is possible to deform the plastic enough to press it down. Short presses turn the backlight off or on. The unit remembers the last setting, but without the backlight, the display is not easy to read, so I don't think I would ever use it without backlight. A very uncomfortable long press allows you to change the alert threshold by waiting until the right digit blinks and then incrementing it round-robin fashion to a desired value. 22 kilowatts is the maximum value. I'm going to test the alert later. Another painful long press brings you out of this through some kind of self-test and back to normal. If you keep the pressure after the set clear appears, you finally get to the function to clear the so far accumulated energy. The unit remembers the consumed energy during power down and restores it when it comes back to life. I think I will use the clear energy function far more than either the backlight or the alerts. Unfortunately, it's the one requiring the longest press. I think this user interface is really only usable with a screwdriver or a similar pointy object to press the button. Enough of testing, let's get inside. 4 crosshead screws are all it takes to lift the back panel off. It looks quite nice and tidy inside. The brain is obviously that big chip covered by the green QC sticker, and to be able to read any markings, that sticker has to go. The PCB is kind of sandwiched between the rear panel and the front. Once the rear panel is removed, it can be simply lifted out, no other screws holding it in place. Next to the LCD, you see the infamous button. It's a bit tricky to adjust the camera and light just right to read the writing, but the big chip is a V9811A. Then we have the S9111, a 7133-1, a voltage regulator probably, a capacitor that looks like a typical Y capacitor, a current sense resistor, a bank of 10 microfarad tantalum capacitors. Notice the track between the two inside terminals? They are connected. Since one pair of terminals goes to the mains and the other pair to the current transformer coil, this means the coil is at mains voltage. Don't touch the coil or its wires and make sure it's not touching anything conductive. So back to the chipset. It turns out that the V9811A is one variant of a family of extremely complex system-on-chip devices developed specifically for the use in electricity meters, and its accuracy exceeds these IEC standards. Lacking the standards, I'm taking their word for it, but I have no doubt it's more than good enough for my purposes. What we have here is basically a microcontroller that has a built-in specialized front end for energy metering combined with an LCD driver. The datasheet spreads to almost 300 pages and it goes into all details which I won't bore you with, but I do want to show you two diagrams. The first one is a block diagram of the V98 family. On the left we have the analog inputs, basically 4 ADCs, and on the far right is the usual microcontroller bus with CPU, memory, flash storage, timers, general purpose I/O, and so on. The interesting bit is this block labeled the Banggood metering architecture. It takes care of all the tricky signal processing to do power measurements, converting to RMS, measuring of active and reactive power, frequency, and so on. It is shown in more detail here. It's quite an elaborate implementation, and it's all done independent of the program running in the processor. I think this is good news for this power meter, because it means all the firmware has to do is read ready calculated values from the hardware registers and display them, so there is not much that can go wrong with the math. By the way, the 3 LEDs on the right in this diagram are used in electricity meters and of course not populated in this module. They show the accumulated energy encoded in form of pulses. I think this is to allow the guy from the electricity company to read the meter by just holding an optical sensor to it. As for the remaining chips, the S9111A implements a very basic switch mode power supply. I found an English translation of the Chinese datasheet, and the only technical data was 90 volts to 265 AC and 5 volts DC out. Interestingly, it seems to work just fine with less than 90 volts. The power meter module itself states 80 volts as a minimum, and I have managed to run it as low as 50. The 5 volts are then fed into the 71331 regulator, which converts them to 3.3 volts for the electronics. I never had the opportunity to play with the current transformer, and I want to do some experiments before putting the meter together. As a start, let's briefly look at what Wikipedia has to say about current transformers. For one, as you can see from the formula, the more windings N the coil has, the lower the current measured by the ammeter. If, for example, the current through the thick wire going through the coil was 1 amp and the coil had 100 windings, then we measure 1/100th of an amp or 10 milliamps. If we use a coil with 1000 windings, we only get 1 milliamp, quite the opposite of a voltage transformer where you get higher voltages the more windings you use. Obviously, we are supposed to measure the current in the coil and not the voltage that is induced. In fact, there's a section here that warns one should not disconnect the burden, that is the ammeter, or you may get kilovolts and arcing. Exciting stuff. The current in the lead going through the coil to the bulb is about 1.4 amps. The BM235 in normal AC volt mode shows about 3.89 volts in the open coil. Because of the high 10 megohm input resistance of the BM235, almost no current flows and it can be regarded as an open circuit. If I select the low pass filter mode for variable frequency drives, or VFD, the same voltage now reads 16.1 volt. Interesting. And in low Z mode, where the input impedance is reduced, the same voltage reads 7.3 volts. Which are we supposed to believe? In this test I have connected my two bench meters, the Agilent 34401A and the Solartron 7150 Plus, in parallel to the BM235. That made the voltage on the BM235 go up slightly to 4.25 volts. According to both bench meters, the voltage is actually 20.7 volts, where the BM235 shows 4.25. Something strange is going on. So I disconnected all the meters and connected a scope probe directly to the open coil. No wonder the meters disagreed on the displayed RMS value. The voltage consists of just spikes. And look at the amplitude. Each horizontal line on the scope is 100 volts, so we have 300 volts peak to peak. I guess Wikipedia was right in warning of high voltage on an open current transformer. You can see how the spikes correspond with the positive and negative half waves, and each high voltage spike is then followed by this oscillation of the voltage settling down to zero. To test what the signal looks like when the current transformer is properly loaded, I connected a 55 ohm resistor across the tip of the probe and the earth clip. Now the signal looks much more sinusoidal, like what you would expect, and the amplitude, which is effectively the voltage across the resistor, is just a bit above the 100 millivolt peak to peak. Using the BM235 in current mode, we can read the current to be 1.46 milliamps. Since the current through the light bulb is around 1.46 amps, this looks like the coil has 1000 windings, if you remember the formula for current transformers shown earlier. To confirm, I use this setup. The module is powered by mains and the current transformer is connected to it, but it also goes through the BM235 to measure the current delivered by the coil into the module. As before, the test current in the lead going through the coil and bulb comes from my AC power supply. I would like to point out that this circuit looks harmless, but because the current transformer is connected to the mains powered module, the coil, its wires and the BM235 and its leads are now all at mains voltage level, and you can easily get a serious electric shock if you're not very careful. If you use the module in an open environment like this, you do so at your own risk. The current through the bulb, at around 1.4 amps before, has dropped slightly to 1.39 amps since the mains voltage is only 233 volts at the moment and my AC power supply is not stabilized. The current readout on the module is indeed 1000 times the current through the coil as measured by the BM235. Okay, it's high time to put this dangerous setup permanently into an enclosure to use it more safely. This is the enclosure I picked after considerable search on eBay, Banggood and other places. This one is from RS-Components and you can get it for £8.30 delivered. It is very sturdy and IP54 rated, which is why it comes with this white rubber seal to fit into the groove around the top that I don't really need. I chose this box because I want to add a UK main socket on the lid, and that needs space and a sturdy lid construction because inserting UK plugs requires quite some force. So those supports in the middle make this enclosure perfect for this. Before starting drilling holes, I did a couple of try fits. The module is slightly wider than a narrow part between the two leftmost supports, so I need to plan for enough clearance on the left. The power socket goes on the right. It will fit either way around, but I think I will put it in that way. For the input, I selected a C14 socket, also known as a socket for kettle leads. For these you need to watch out, because many cheap ones are not rated for high currents. This one has one of the highest current ratings I could find. It is marked 250 volts 10 amps following VDE standards and 250 volts 15 amps following UL. Take your choice. Given that UK main sockets are usually 13 amps max and I don't plan to go that high anyway, it should be okay. If you do lots of high power stuff, a better and cheaper alternative is to use a trailing wire and a UK mains plug for the input, but I wanted a clean box that stores away without having cables hanging out of it. I used a side view to test for the depth of components and arrangements of the coil and the C14 socket. In case you're wondering, the outlet sits temporarily on an eraser to allow me to positioning it without falling over all the time. Of course, the eraser is not going to be part of the build. I considered putting the C14 socket on the other side under the module, but then it gets very close to the screw terminals of the module. 2 hours later and the holes are cut, filed reasonably smooth and the components mounted. I want to mount the current transformer on the underside of the lid in a gap between the module and the power socket. Keeping it all on the lid greatly simplifies the cable runs. I made this little wooden bracket that will be glued on the lid, and 2 plastic cable ties through the holes on either side will secure the current transformer. It is important not to use conductive material to avoid causing short circuit loops. All wired up. I used 1.5 mm flex rated 16 amps to wire the connection from the C14 inlet to the outlet socket. The brown live wire goes through the current transformer. Thinner but still mains rated wires connect mains to the module, and the original wires of the current transformer are just long enough so no ugly extensions are needed. For a first test, I plugged in a fan heater. At first only the fan is running, which draws 180 milliamps and uses about 33 watts and has a power factor of 0.74. When I turn on the heater, the current jumps to 4.4 amps and consumed power is now 1 kilowatts plus the power of the motor. The power factor is now 1 because the large resistive load drowns out the tiny amount of apparent power caused by the motor. With the fan heater still plugged in, it's a good time to test the alert feature. I have set the threshold to 0.3 kilowatts or 300 watts. When only the motor runs, consuming 33 watts or so, the display is like it was before. But when I turn on the heating coil, the 1 kilowatt causes the display to start blinking. Since there's no speaker or beeper, blinking is all you get. It stops when the power drops below the threshold. The alert feature is always active. To avoid being bothered by alerts, you need to set it to a really high threshold. Some more tests. Here's an energy-saving fluorescent light bulb rated for 11 watts. As you can see, it's pretty much spot on, but its power factor at 0.64 isn't great. This next test case is a LED light bulb nominally rated for 8.5 watts. It is drawing 9.2 watts instead, with a pretty terrible power factor. This bulb has a built-in dim function. If you turn it off and quickly on again, it dims to 40%, and repeating this again reduces it to 15%. It is now running at 3.64 watts, which is indeed 40% of 9.2 watts. The camera doesn't do this justice because the light is indeed much reduced. And now it's down to 1.51 watts. The current has dropped below the measuring threshold, so the power factor is shown as 1, although it probably isn't in reality. I was about to finish this video when I thought of a way to test the frequency display. In this setup, my function generator is set to 50 Hz sine, driving an amplifier you see on the left. The amplifier speaker output feeds the secondary winding of the blue transformer in the middle. Because the impedance of the transformer is too low, the 4 ohm power resistor is in series with the transformer. The 2 times 115 volt primary windings are in series and feed the power meter with about 60 volts through the C14 input and the multimeter, which is set to Hertz. I can drop the frequency on the function generator. As you can see, the power module does show the correct value. This works all the way down to 29 Hz, but anything lower causes the frequency of the power meter to fluctuate. But if you go back up to 29 Hz or higher, it shows again the correct value. Let's see how high we can go. No problem, of course, going to 60 Hz. 70 Hz, 80 Hz, no problem. 90 Hz, still good. Okay, 99 Hz is the maximum display. It just stops there even if you go higher. After I succeeded in testing the frequency display, I wondered if I could verify the power factor too. This is much harder. In the end, I used this setup. As before, the blue transformer is producing the AC voltage going into the power meter. I need to go to almost 100 volts to get enough current to flow, which makes this quite dangerous, so if you try this, you do so at your own risk. Basically everything in the red dotted box, including your scope, is at that high voltage. The output of the power meter is connected to a capacitor of 1 microfarad in series with a resistor of 1.5 kilo ohm. Although I used a 1 watt resistor, it is quite overloaded and it gets very hot very quickly, which is why I can run this only for a few seconds at a time. There are 2 scope probes connected, channel 1 tapping between the resistor and the capacitor, and channel 2 on the other side of the capacitor. Together with a common ground for the scope, channel 1 measures the voltage drop across the resistor, which is therefore equivalent to the current flowing in the circuit, while channel 2 measures the voltage across the whole circuit. You can see the transformer providing the isolated high voltage going into the input socket of the power meter. The capacitor and resistor circuit is connected to the output, and you can see the scope probes and the black lead are used to connect the common scope ground. On turning the power on, the meter shows a current of 30 milliamps, 1.45 watts and a power factor of around 0.51. The yellow trace of channel 1 is the current and the blue trace of channel 2 the voltage. The purple line is channel 3 of the scope, which isn't connected, but I turned it on as a neat trick to get a very visible zero line on the display. I have automatic phase measurement turned on, and on the bottom left you can see the phase difference of around 56 degrees. Let me turn on statistics to make it a bit more prominent. The yellow current trace is leading the blue voltage trace by around 56 degrees. The current leading the voltage is what you would expect for a capacitive load. The cosine of 56 degrees is 0.56, which is in the same ballpark, but a bit higher than the 0.52 shown on the power meter. Maybe the automatic measurement is a bit off due to the slightly distorted waveforms after passing through 2 transformers. So let's measure it manually using cursors. Basically we need to measure the time difference where the 2 curves cross through the zero line. So I move one vertical cursor to the point where the blue curve crosses. And then do the same with the other cursor for the yellow curve. The only thing we are interested in is the BX minus AX readout, which is 3.28 milliseconds. To convert this into a phase shift angle, divide the value by the duration of the full period, which is of course 20 milliseconds for 50 Hz AC, and multiply the result with 360 degrees. This calculation produces 59.04 degrees. The cosine of 59.04 degrees is 0.51, which is just what the power meter showed. Not that I had any doubts that the chip in the power meter would be able to measure the power factor correctly, but it's nice to have it confirmed. Well, and there you have it, my poor man's Popey meter. Module and enclosure and sockets were about 25 pounds delivered. For me, it's certainly good enough, and I found experimenting with a current transformer and measuring the power factor very interesting. I leave a list of parts used in the description below. If you liked this video, give it a thumbs up and feel free to comment. Thanks for watching.